All right, today we're going to crack the code of one of the most brilliant, most elegant tools in all of science, the periodic table. And trust me, it is so much more than just a poster you see in a chemistry class. It's basically a guide to the entire universe.
Now really, just think about that for a second. What if you had a single map that could tell you the secrets of, I don't know, the air you're breathing, the device you're watching this on, even the stars in the night sky? What would a map like that even look like?
Well, it would look exactly like this. This isn't science fiction, it's not a fantasy map, it's the periodic table of elements, and its amazing, elegant structure holds the fundamental rules for literally all the matter we have ever discovered. So let's start breaking it down.
Okay, so first things first, let's look at the basic layout. The way this whole thing is organized is not random at all, it is a work of pure genius.
The modern table you see here organizes elements by their atomic number. And all that means is the number of protons in an atom's core. Each element just has one more proton than the one before it. That simple rule is the foundation for everything else that follows.
So, this map has two main coordinates, right? The vertical columns are called groups. The best way to think of these is as families. Every element in the same group acts in very similar ways. Then you have the horizontal rows, and those are called periods. Everyone in the same period has the same number of electron shells, which is kind of like saying they all live in the same floor of a giant apartment building.
But why? Why do these families act so much alike? Well, the answer is a hidden code that, you guessed it, all comes down to the electrons.
And the key to this code is something called electronic configuration. Now that sounds super technical, but it's really just a shorthand for describing how an atom's electrons are arranged in their shells. And this arrangement, well, that's what decides an element's entire chemical personality.
And here's the best part. You don't need to memorize it. An element's address on the map, its group and its period, tells you everything you need to know about its electrons. It's like a cheat code.
Let's see how this works. We'll use sulfur as an example. Okay, step 1. Find its group. It's in group V. Boom. That means it has 6 electrons in its outermost shell. Got it. Step 2. Find its period. It's in period 3. So it has 3 electron shells in total. You put it all together and you've cracked the code. Sulfur's electronic configuration is 2, 8, 6. It really is that simple.
Now that we can actually read the code, let's meet some of the table's most famous families and see how their address on this map perfectly predicts their personality.
So, way over on the far left, in Group I, we have the alkali metals. These are the rock stars of the table. I mean, they are highly reactive. They're so soft you can literally cut them with a knife, and they are so desperate to react with air, they have to be stored under oil just to keep them calm. And their reactivity, it gets even more intense as you go down the column. And the reason is that their single outer electron gets further from the nucleus, which makes it way easier to just give away in a reaction.
If you want a perfect example of what I'm talking about, just look at potassium. When you drop a piece of it in water, it doesn't just fizz a little. No, it bursts into this beautiful, violent lilac flame. That is exactly what we mean when we say reactivity increases down the group.
Now, let's jump to the complete other side of the table, over in group 7. Here we have the halogens, and they are pretty much the polar opposite of the alkali metals. They're nonmetals, they hang out in pairs as diatomic molecules, and their reactivity trend is completely flipped around. It actually decreases as you go down the group. That's because the larger atoms at the bottom just aren't as good at attracting that one electron they're missing.
And you can literally see this trend just by looking at them. At the top of the group, chlorine is a gas. You move down one step to bromine, and now it's a liquid. You go one step further down to iodine, and it becomes a solid. It's this clear, predictable pattern, and it's all based on their position on the table. So cool.
So let's put them side by side, just to make it super clear. For the alkali metals over in Group I, the action gets way more intense as you go down. For the halogens in Group 7, it's the elements at the top that are the most reactive. 2 different families, 2 totally opposite personalities, and it's all explained by their place on the map.
And finally, all the way over on the right, in Group 8, we have the noble gases. You can think of them as the VIPs of the chemical world. They have a completely full outer shell of electrons, which makes them so perfectly stable and content that they barely react with anything at all. They are the cool, aloof celebrities of the table.
Of course, no map is absolutely perfect, right? And the periodic table has its own wildcards. These are the elements that don't quite follow the main rules so neatly.
Smacked right in the middle of the table are the transition metals. These are your quote-unquote typical metals like iron, copper, and gold. They have high melting points, they form all sorts of beautiful, colorful compounds, and they are fantastic catalysts, which means they're great at speeding up chemical reactions. They also have this neat trick called variable oxidation states, which just means they can form ions with different charges. And that flexibility is what makes them some of the most useful elements we have.
But maybe the biggest puzzle on the entire map is the very first element, hydrogen. It is so unique that chemists to this day still kind of debate where it truly belongs.
Okay, so here's the dilemma. On the one hand, hydrogen has one outer electron, just like the group I alkali metals. So, okay, maybe it belongs there. But on the other hand, it only needs one more electron to get a full outer shell, just like the group 7 halogens. It even forms paired H2 molecules just like they do. So, where do you put it? It's the ultimate chemical enigma.
So after all that, what is the big takeaway? What's the point of all this? Well, it all comes down to the incredible predictive power of the table.
The table isn't some static list of ingredients you find in a recipe book. No, it is a dynamic tool that allows scientists to predict how an element is going to behave, sometimes before they've even seen it.
And that right there, that is its true genius. By simply knowing an element's address, its group, and its period, you can make unbelievably accurate predictions about its reactivity, what it looks like, and how it's going to interact with everything else in the universe.
And this map? It isn't even finished yet. Scientists are constantly creating new elements in labs. The last 4 were only officially given their names back in 2016, which really makes you wonder, doesn't it? What new discovery is waiting just around the corner that's going to redraw our beautiful, elegant map of everything?